Let's take a look at what happens to the equilibrium concentrations of an acid-base solution when I change the pH. Let's first imagine that we have an acid in water. So we'll write the acid ionization reaction. HA plus water forms the conjugate base plus H3O plus, and that has an equilibrium constant of Ka. When I increase the pH of this solution, that means that I will decrease the H3O plus concentration. So remember that pH increasing implies that H3O plus has decreased. So if I decrease the amount of H3O plus in my solution, I can think about what Le Chatelier's principle tells me about what will happen. So Le Chatelier's principle tells me that I will need to make more H3O plus because I've removed H3O plus from solution, and so my reaction is going to shift in this direction, which means that the HA concentration is going to decrease and the A minus concentration is going to increase. And so if I increase the pH or remove H3O plus from solution, I'm going to increase the amount of conjugate base and decrease the amount of conjugate acid. Conversely, if I decrease the pH, that would be the same as increasing the amount of H3O plus in solution. And if I do that, I can see Le Chatelier's principle tells me that I'll need to use some of that up, and so the reaction is going to shift in this direction, causing the A minus to be used up and the HA to be made. And so as I decrease the pH, I will increase the amount of conjugate acid and decrease the amount of conjugate base. If we think about the expression for Ka, it's equal to the concentration of H3O plus times the concentration of the conjugate base divided by the concentration of the conjugate acid. If I happen to have an H3O plus concentration that is equal to my equilibrium constant, so in other words, if Ka is equal to the H3O plus concentration in my solution, I know that pKa is equal to pH. So in other words, take minus the log of both sides of this equality, and pKa equals pH. So if I happen to make up a solution such that the pH is equal to the pKa, then I can rearrange this equation and I can see that 1 is equal to A minus divided by HA. And so the ratio of the conjugate base to the conjugate acid is equal to 1, or I can say that the conjugate base concentration and the conjugate acid concentration are equal when pH equals pKa. So if we imagine the range of pH values that this solution could have, there's a value of pH in the middle where the pH is equal to the pKa. And then we have values of pH that are greater than pKa and values of pH that are less than pKa. So here pH is greater than pKa, and here pH is less than pKa. Notice that if I'm in the middle, that I will have a composition of my solution such that my conjugate acid and my conjugate base have the same concentration. However, if I am at a pH that is less than the pKa, so my solution is more acidic than the pKa, i.e. I have added H3O plus, that will cause the reaction to shift in this direction and make more HA. So over here, where the pH is more acidic than the pKa, smaller than the pKa, my HA, my conjugate acid concentration will be greater than my conjugate base concentration. On the other hand, if I'm in a regime where my pH is more basic, pH is greater than pKa, then that will be as though I have removed H3O plus from solution, causing my reaction to form more conjugate base. And so over here, I will have more conjugate base than conjugate acid. We can make a similar argument when we put a base in water to form the conjugate acid of that base plus OH minus. This equilibrium reaction has an equilibrium constant of Kb, the base hydrolysis reaction. Notice that when the conjugate acid concentration times the OH minus concentration divided by the conjugate base concentration is equal to Kb, and so when we have the OH minus concentration equal to the Kb concentration, we will have equal concentrations of conjugate acid and conjugate base. And so we can do the similar kind of number line where we have POH equal to PKB will imply that the conjugate base concentration is equal to the conjugate acid concentration. And if our POH is less than Kb, then that means that we will have a larger concentration of OH minus in solution. So if we increase this OH minus concentration, we're going to want to try to use it up, and so we're going to make more of the base. And so over here, we're going to have a conjugate base concentration that is greater than a conjugate acid concentration. And if we have a POH that is greater than the PKB, then we will have a smaller OH minus concentration, and so our reaction will try to make more OH minus and make more BH plus, more conjugate acid in the meantime, and use up some of the conjugate base, and so we'll end up with a conjugate acid concentration that is greater than the conjugate base concentration. Notice that when I drew these number lines, I put the larger POH at this end to correspond with the smaller pH. Remember that as pH goes down, POH must go up. And I put the smaller POH on this side to correspond with the larger pH, because again, as POH goes down, pH must go up. So that puts these two number lines in the same direction, in the same order.